Hello everyone, welcome to my Semester 1 project overview video for my Engineering Architecture 3 class at Joliet Central High School. I'm Jose Lara and I will be narrating you through my two major projects I've done so far this semester and a bunch of mini projects I've done. And I'll be providing an explanation of all my projects, design and choice insights, and a reflection for these projects individually and the semester as a whole. The first project this semester was a 3D printed glasses case. Starting off with the glasses case project, I began with closely following the engineering design process. I started off the project by defining the problem. My problem was the design of my old glasses case at the time. The case was too large and the shape was too difficult to hold, organize, and carry around inside a backpack, and I wanted to make my own design that didn't have these same design issues. Once I clearly indicated the problem and gave my reasons, I moved into researching different case solutions. I looked into materials and their different circumstances, what kinds of materials were best in handling certain situations and environments. I found out that the hard materials were to prevent the case from breaking from any kind of force, but what I mainly focused on was the materials that fell under the semi-hard category. These materials are used for their lightness and flexibility, allowing the case to be easily portable, light, and flexible. Something that I would use that would solve one of the issues I had with my previous case. I also researched the size and shape. Glasses cases were tailored specifically for one kind of glasses were by far the most effective. Large cases typically tend to suffer from the problem of the glasses inside bouncing around, which could damage the lenses, while small cases would bend the glasses frames. My best bet was to make this case specifically for the glasses I use. To cap off the research, I looked into the different types of cushioning. I figured out that my design should be padded with foam pads or fabric linings to protect my glasses from potential scratches. The second step of the engineering process is the generation of concepts. I proceeded to create two possible different case designs with different mechanisms. The design on top, shown in the image of my engineering notebook, is a triangular design. This case design is very peculiar. The case was made up to two pieces, one on the inside and one on the outside, and utilizes a hook to open and close. The two pieces will use a magnetic force from two magnets to remain closed. These magnets will hold the two pieces together, which would be on the case, where the glass were held, and the protective shell, to make sure the case holding the glasses wouldn't fall out where you're pouring them places. The other design, the other design shown on the bottom is a rectangular design. This design would be your more traditional glasses case and would utilize a H mechanism to open and close from the middle. Both of these designs would include things such as fillets and interior fabric linings for cushioning. These cases will also be both made out of carbon fiber PLA plastic. The case design I would end up going with will be my triangular case design. Not only are triangles naturally stronger shapes than rectangles, but I also felt that this design was more creative, utilizing magnets and a hook opposed to traditional hinges. After choosing the design I wanted to go along with, I began to develop a cardboard prototype to test out size dimensions and how I wanted my finished product to look like. I used Autodesk's AutoCAD to design the sides and the faces. I began by modeling the size of the triangular face I wanted, then followed it by projecting the lines to give me the rectangle pieces and will go on to give me the sides of the triangle. Then I took the drawing that I made in AutoCAD and used a classroom laser cutter to cut a piece of cardboard into the shapes of the pieces I drew. I got all the pieces and assembled them together with tape, but I made sure not to close the triangle completely to see if my glasses were capable of fitting in. And as you can see in the picture in the bottom, the cardboard prototype was unsuccessful and the case was not long or deep enough to hold my glasses comfortably. After the failure of my first prototype, I moved into designing my next prototype. This time, this prototype was going to be 3D printed. I began the model in Autodesk Inventor by starting with the model of the previous size dimensions of the cardboard prototype before modifying them accordingly to be big enough to hold my glasses. Soon after modeling the case, I modeled the shell that would cover the case. The prototype was another failure. As seen on the bottom left picture, the miner wasn't deep enough to fit my glasses, so my glass would stick out. But on the bright side, the prototype was long enough to fit my glasses, which meant that I now knew the length that my glasses case would have to be. So, for my next prototypes, in order to save on material and time, I 3D printed bite-sized pieces of actual model instead of the entire thing. What I did was cut off majority of the case, leaving one of the faces and a little bit of the body sticking out. Another thing I did to save on material was lower the filling filament, which means that the pieces would be hollow while still being structurally accurate for testing. This would save on material. I used this piece to test how to see if my glasses case was deep enough to fit where my glasses could fit in properly. Alongside it, I 3D printed a piece of the shell that would cover the case to see if the two pieces would end up being able to slide inside together without issue, which did end up happening. If you see in the image on the far right, you can see the prototype was a success. Both pieces slid right through each other perfectly, and the prototype passed the depth test. My glasses were able to fit in comfortably inside the case piece. Now that I had everything in check and all the prototypes had given me all the necessary dimensions for the final product, I updated all the models and added in holes for the planned magnets. Right before 3D printing, I grabbed the models I made for both pieces and made an assembly in Inventor. This assembly was to check to see if all the pieces fit correctly without any issue, for an extra precaution. After everything checked out, I began the 3D printing process. I set the 3D printer to use carbon fiber PLA to print out the drift of my design. Now, something you can't see in the picture is the hole for the magnet in the shell case. It's located very deep in the very deep end of the case that is sitting upright in the picture on the right. It would be very difficult to get the magnet inside of the hole if I were to put it once I was done 3D printing. So what I did in order to get the magnet in there was to program a pause in the 3D print. The pause would happen right away after the hole was done printing, but before the walls began being printed, which left an easy access point to the hole, and continued after the magnet was placed inside. I also used tree supports to help the case piece on the left not collapse onto itself during the print. After removing the tree supports, I tried inserting the magnet inside the hole on the back, but it couldn't go in. The hole I made for the magnet was already super tight due to my small tolerance, but the tree residue present in the hole made it impossible for the magnet to fully go in. The picture on the bottom right shows you how the magnet sticks out. No matter how hard I tried with pliers, I couldn't get the residue out. But aside from the magnet issue, the case worked perfectly as intended. And since the shell functioned as it was supposed to, that meant I can reuse it, and the only piece that needed to be readjusted was the case piece. So the only thing stopping me from having a functional case was the diameter of the magnet hole in the back of the case piece. So what I did in order to get the correct diameter size required for my case was to 3D print a bunch of small holes on little blocks with varying tolerances, the diameter to test out the best tolerance. After a couple of tests, I eventually found that the best diameter for my case was a diameter of zero point 0.6 inches, which you can see in the second last block and the image on the bottom right. After fixing the diameter of the case, it was time to 3D print the case piece one last time. The print was a success. The magnet slid in perfectly and snugly with little force required. The 3D printed glasses case was now, for the most part, complete. Now, before I play my video, let's give you a quick overview of my glass case design, again to refresh your memory. My 3D printed glasses case design consists of two triangular parts: the actual case itself and the protective shell. The case is supposed to slide in into the shell and stay inside thanks to both magnets sticking together due to the magnetism force. With the hook present in the opposite face of the magnet hole, you're able to pull out the case from the shell with ease. The case was filleted in order to remove the possibility of the case stabbing anything such as notebooks or other objects around it. The interior of the case is meant to be lined with fabric in order to keep the glasses protected from scratches, and the entire case is made out of carbon fiber PLA plastic. The video I'm about to show you is a video that showcases the functionality of my case. While my glasses case were functional at the end of the day, it was nowhere near perfect. One small concern that I have on the magnet in the back of the case piece is I forgot to add the super glue to stick the magnet inside the hole. This is the only concern that is a human error in the construction process. I would have applied glue before testing to see if the magnet was capable of fitting inside the new hole diameter. But this issue could be easily fixed if the magnet were to ever fall out. The next issue in my design is cushioning. Because the case was designed to be as tight as possible to avoid potential bouncing, that meant that I don't have a lot of interior space to work with. Because of this, I have a limited amount of options for fabric lining to use for my cushioning. Fabric lining might cause my glasses to stick out and not fit anymore. The only solution to this would be making the glasses case larger in size. The last issue for the glasses case is the tree support residue. For some reason, during the printing of the new glasses case piece, the top corner of the case piece spaghettied. Though, like the magnet issue, this can be easily fixed with with the use of sandpaper and melting the pieces smooth with a lighter to make the surface smooth. But now that the 2 months have passed, I can safely say that my glasses case design is effective in everything I could ever want in a glasses case. My glasses haven't been scratched, nor my frames bent. Even despite the lack of cushioning, I would consider this project a success. Now that I have evaluated my design, I am going to evaluate myself and how I handle the engineering process. During the making of the presentation, I noticed a lot of issues I faced throughout the designing of my glasses case were caused by my lack of prototyping and testing. If I were to prototype more often, I would have spotted the magnet hole error earlier and saved a lot of time and filament. But I can't go back anymore, and the only thing I can do now is apply what I learned for the next project in the future. So from now on, I'll be prototyping more often to avoid the same mistakes that I made during this project. Moving on to the second and final major project of the semester, I present the rubber band powered vehicle project. Beginning with the first step of my engineering design process, the problem is defined. My project is a 2025 Skills USA Illinois State A-League Career Competition problem for their additive manufacturing sector. For this problem, I have to create a fully 3D printed four-wheeled vehicle capable of traveling 6 to 12 inches using the elastic potential energy from a rubber band as its only energy source. According to the most important design requirements, my design is to be fully 3D printed, cannot contain outside hardware, must have at least 3 moving parts, have wheels with a diameter of 3 inches, be powered by a single rubber band, and must not exceed a 6 by 4 by 4 inch size constraint. The image below demonstrates an example of what my design should look like. The research part of the engineering process began with defining several design considerations. Most, if not all, were ones that I wouldn't use. So I learned two very important things from my vehicle body research. One, the teardrop is the best shape in reducing drag, and the second being that different kinds of aerodynamic shapes. Specifically, something I would touch upon is the shape of the vehicle. A teardrop is more aerodynamic than the shape of an F1 racing car, which might be surprising for some. It certainly was for me. The reason why I should have a teardrop shaped vehicle is because F1 racing cars lose turbulent airflow in order to boost the vehicle's downforce, which is the force that helps the car remain on the ground. And since my vehicle won't be traveling 233 miles per hour, it will be better for me to choose a teardrop shaped opposed to the shape of an F1 racing car, because a downward force would hinder my vehicle instead of helping it be more aerodynamic. Moving on to my rear research, my research mainly focused on back tires opposed to car tires. This is because I wanted to go with thin tires. Learning the dynamics of thin tires, like the ones on bikes, would be more beneficial in this situation than researching the dynamics of a car tire, which are much heavier and bulkier. The main things I took away from this research are spokes and tire treads. To avoid potentially not gaining enough traction, my wheels need some kind of blocks or sipes tread patterns. I decided to go with straight radial lacing spoke patterns combined with a symmetrical groove tire pattern with bladed spokes. While bladed spokes would have been the best, I decided against it because I feared that the 3D print residue would harm the inside of the wheel. So, in order to be safe and keep the wheel movements smoothly, I went along with the straight spokes, something that I knew wouldn't leave residue. My gear research was the most extensive research simply because my design required at least two moving parts, of which gears were the easiest to implement. So, after researching different kinds of gears and their uses and mechanisms, I learned all about the features of a gear and different gears that they have from one another. I decided that the spur gear was the only kind of gear that was applicable to my design that I was creating. Long story short, other types of gears required angles and mechanisms that would not be present in my design and would honestly overcomplicate my design, which will only hurt me by adding more weight than functionality. After finishing up my research, I moved on to the third step of the engineering design process, which is the generation of concepts. I generated broad sketches of what I wanted my design to look like because I thought a teardrop vehicle would be too hard to translate over to a four-wheel design. I ended up with a horseshoe shaped body with the ends sticking up to make room for the large wheels. My wheels are going to have the same features, just different diameters. I planned on only having four spokes with grooves surrounding the perimeter of the wheel. For my gears, I was planning to make the small gear my input gear and the large gear my output gear. This is due to the fact that a small input gear driving a large output gear results in more torque, which is a force needed to travel long distances. The planned gear ratio between my two gears is a 1 to 3. Something about the holes in my gears and wheels is that they have two keyways at both ends of the hole. This to make room for my axles, which would have keys that fit into the keyholes. This was done to make sure the gears and wheels were being rotated alongside the axles to avoid the axle spinning by itself without pushing these features, which results in my vehicle not moving at all. When I moved on to the next step, which is developing a solution, I jumped into Inventor and began modeling my parts that I sketched. My body remained at a 101 from my sketch, keeping the same features and the same three hole placements, which would be for my axles to slide in through. My wheels underwent a few changes from my sketches, primarily the spokes and grooves. Instead of four spokes, I decided to add another spoke for the structural stability. These wheels would have to carry the weight of my vehicle after all. The spokes of my design also changed to be bigger. They resulted in this spiky pattern along the wheel, which is different from the more blocky pattern of my sketch. This is the only feature that remained relatively unchanged was the double keyway holes for the axle. Just like the body of the vehicle, the axles didn't undergo any changes. The only thing that was new, and none of the original sketches, was my gear axle. The gear axle is just like a normal axle except shorter and with a hook where the rubber band can hook onto. The keys remained unchanged. The biggest change in my gears were the gear ratio. In my sketches, the gear ratio was 1 to 3, but in the gear ratio of the model is 1 to 2. I changed the gear ratio because I thought the new gear ratio would have better engagement with the energy provided by the rubber band. This is what my vehicle design looks like and is planned to look like once assembled in Inventor. I used joints to assemble the vehicle together. For some reason, I kept getting error messages when I kept trying to use constraints. So my Inventor assembly does not move at all like it's supposed to. With my models all finished, my next step is to construct the prototype. I'll need a 3D print every piece and assemble the vehicle together, testing out its efficiency and see where changes need to be made. Once the 3D print was finished and assembled, I noticed that the tolerance between my parts wasn't tight enough. So in order to stop everything from falling out, I quickly modeled and 3D printed C-clips. After installing the C-clips, my vehicle was ready to stand on its own. When I got to testing the vehicle, everything was a failure. The gears couldn't mesh because the gears couldn't touch because of the height differences between the axles. I didn't notice this issue because inside Inventor, the gears were floating along the center of the hole, but in person, I failed to account for gravity. So the axle was positioned on the bottom of the hole instead of the middle like an Inventor. Another issue they ran across was the wheel traction. The wheels would spin in place without pushing forward on the ground to propel itself. The last big issue was the movement along the axles and gears. This movement made it very difficult for the gears and axle to align together. Some changes need to be made. In order to solve the traction issue, I updated the wheel treads to be rounder instead of spikier in hopes that this would increase the grip of the tires they would have on the ground. To adjust the unwanted moving parts in the gear height difference, I made the axles thicker. This would lift up the gears and make tolerances tighter, which would help reducing unwanted movements. Despite all my previous changes, it was all in vain. My vehicle continued to spin in place, and the C-clips couldn't address the movement problem. It only made it less frequent, and sometimes even caught with the back tires. So, with the suggestions of my teachers, I made the wheel treads longer. This would increase the amount of contact that the wheels had with the ground, which would make it easier for the vehicle to have more surface area on the ground to push forward onto. The last thing I wanted to change was the tolerances. I get rid of most of the C clips and instead make my pieces have a tolerance of 0. This will make C clips obsolete. This update required me to reprint every piece aside from the body. After the design was done printing, I assembled it together and immediately got to testing. This design of the vehicle was functional. The new treads allowed the vehicle to propel itself forward and move, and there was zero issues with any parts locking up or interfering with each other unintentionally. This video showcases our project and how it works, and that is evidence that the vehicle is functional and able to be displaced within 6 to 12-inch range. Alright, so I'll be explaining to you how my project works. First, you're going to need a rubber band, and you're going to tie it by pulling it through, opening it up, and then pulling this end through the hole, and then that's how you're going to tie this. So how this project works is that, so if you see here, there should be a nook for this rubber band to go inside of. So once this goes inside, I'm going to spin this, the gears, and the axle, and I'm gonna spin this until the rubber band is like all the way stretched out. And afterwards, what I'm gonna do is I'm gonna let go, and that's gonna cause the axle and the gears to like start moving. And these back gears will be aligned. So the front gear, these gears spin the back gears, and because these back gears have zero tolerance with the axle, that would mean the axle will spin along with the gears. And because the wheels also have zero tolerance with the axles, the wheels will spin along with the axle. I have some C clips, two C clips, just to keep the this middle axle from shifting. But yeah, so I'm gonna from 11, and this is meant to go 6 inches. So this should go from 11 to 17. So I'm gonna wind it up. See that it's in there. Now I'm just gonna pull it. Position it. I'm gonna start at 11, and it should go to 17. It moved at an angle, but as you can see, it went past 17, meaning that this vehicle is capable of moving past 6 inches. My project, that's how it works and how far it travels. This shows that it meets design requirements. Let's quickly overview my design before the evaluation. My design was to be fully 3D printed, met the 4-wheel requirement, contained 8 moving parts, 4 wheels and 4 gears, used a single rubber band, and was capable of traveling 6 to 8 inches. Used elastic potential energy to kinetic energy conversion, and used zero adhesives, and was within the 6 by 4 by 4 size limit. I am very happy with how the vehicle turned out, but there was definitely some room for improvement. For example, there is a bigger difference in the wheel thickness between the output and the input gear. It would have made it easier for the two gears to mesh together. Meshing in my current design works good enough, but it would have been easier. Another thing I could have done differently was the wheel treads. While being functional, I believe that the current wheel treads are in the optimal shape, and there could have been some combinations out there that I would have loved to play around with to figure out which one gives me the best traction. Moving forward, my gear axles shift back and forward and require two C-clips to hold in place. If I had changed the shape of the axle, I could have definitely made the C-clips obsolete in the design. Making the keys thicker would have possibly made this harder for the gear's axle to shift. Another positive change would have been the wear reduction in the body of the vehicle. If the vehicle was made thinner, it would have been less weight and less friction, which would have allowed the vehicle to travel further. Finally, the back of the wheels shift around, similar to the gear axle. If I were to make the keys thicker, just like in the gear axle, this movement wouldn't happen. Now that we reviewed all my projects throughout this first semester of Engineering Architecture 3, I would like to reflect on my performance this semester. My time management this semester was inconsistent. During my first project, I was making progress daily, but I began to slow down during the second project. This was because my motivation for the second project was beginning to fade out, and I did many smaller projects to take my mind off of it. Another point of reflection is the creativity of my projects. Something I liked most about my projects was the way they challenged me and helped me grow as an engineer. My first project challenged my thinking. I came up with something out of the norm, which was my case design, and went along with it. While my second project challenged my understanding of physics behind mechanisms and helped me lay a foundation for my understanding of gears and energy transformation in engineering. I also liked how my projects were applicable to the real world. Designing a glasses case is something engineers do. They research and test out different products for their utility and simplicity for consumers. The rubber band powered vehicle is a mechanism for how they wind up toy cars, toys that engineers design and produce. Something I want to do differently next semester is the types of projects. I aim to do a team project next semester. Working with others is an integral part of the engineering as a field. So gain experience of it now would help develop my communication skills with others and help tackle more complicated projects. Something else that I would like to do is to take more videos of my projects. Videos that show and videos that showcase how the product works and its capabilities under certain conditions. Finally, I want to be more consistent with updating my engineering notebook. I update it in waves instead of daily, like I'm supposed to. I'll aim to update my engineering notebook after progression milestones that have been reached. Something I've also been lacking is the working CAD drawings for my projects. I still haven't made the CAD drawings for my glasses case. But next semester, I'll make sure to make the drawings during the periods where I am waiting on 3D printer while I'm practicing for technical drafting competitions such as IDA or Skills USA. Before we end the presentation, I would like to showcase the smaller projects I've done throughout the first semester. For the first mini project, I have created laser cut keychains for the Joliet Central Science Club Jeopardy game. I used AutoCAD to trace and attach images that correspond to Jeopardy game subjects. For example, astronomy was one of the categories, so I designed an Earth keychain. This was done for every theme. An AutoCAD feature that I utilized was line weight, instead of using Hatch to make it easier on myself. Using Hatch would require me to offset the drawing entirely and the curved feature separately. Using a thicker line weight avoids this tedious task altogether. Moving on, CAD Adventure Fridays are a day of the week, Friday, where Engineering Architecture 3 class spends their time doing CAD practice problems for the upcoming CAD competitions at Joliet Junior College, IDEA, and Skills USA over at Peoria, Illinois. My first CAD Adventure Friday project was a gyroscope. This is the image on the far left. This assembly tested my constraining skills. One part could have multiple constraints on different parts. And for my next project, I was doing the 2015 Skills USA pulley practice problem, where I modeled individual parts and started the assembly. This practice set tests my modeling skills, technical drawing comprehension, and assembly skills, and my ability to work faster. Well, that's all. That was my semester one overview and reflection. Thank you for watching.